So thank you very much. First, as someone who has been on Blue Waters for a while, let me take the opportunity to thank NSF for providing us with two successive pre-reg grants and the Blue Waters staff and all kinds of assistance. And I'm going to talk about the subject of turbulence, and part of the talk will be by my graduate student, Matthew Clay, standing by. And I'd like to talk about what we call extreme events and the importance of resolution, and also we will be talking about a parallel algorithm for studies of turbulent mixing. Is there a remote? Yeah, I'll have to use mine. Pointer. Okay, thank you very much. So, as some of you may know, the main characteristics of turbulence is that of disorder and therefore a lot of uncertainty. The fluctuations can be unsteady, they're always unsteady, three-dimensional. They go over a wide range of scales, and they're also nonlinear. And turbulence is very common in many fields of science and engineering, and many times effective mixing, like what we see in the picture. On my back at page 1 now. Something wrong. Okay. So how do I point them? Sorry. Oh, thanks. Okay. So in the picture on the left here, what we see is essentially chemicals mixed with each other. This is the case of a turbulent jet. In the middle, you have a submarine. And on the right-hand side, you have a vortex rolling up from the back of an airplane that is taking off from the runway. In many situations, the non-dimensional parameter known as the Reynolds number is very high. And the Reynolds number is when the Reynolds number is very high, we have a wide range of scales. We have a lot of uncertainty, or you can say we have a large number of degrees of freedom, and therefore, correspondingly, we need a more powerful computer. Okay, so in the first part of the talk, the rest of the talk, I'm going to talk about extreme events and how we resolve the small scales and why it is so important. And our emphasis is on what happens in turbulence at high Reynolds number. And we're going to focus on the fundamentals. We have an idealized geometry. We're going to use Fourier pseudo-spectral methods, which benefits a lot from network topology, in particular topologically aware scheduling that the Blue Waters staff developed a couple of years ago. Our simulations are up to a good resolution of 8192 cube, which is half a trillion. It was data 16K cube, which is essentially 4 trillion grid points. Some of our results have appeared in a paper proceedings of National Academy of Science in 2015. The second part of the talk, we'll talk about more recent work with more emphasis on the algorithms. When we talk about turbulent mixing of substances with low molecular diffusivity, this essentially becomes a multi-resolution problem, suggesting that it would be profitable to use different approaches for the velocity field and also for the scalar. And we're going to for the scalar, we're using compact finite difference schemes, and we have some advanced uses of OpenMP, which have been found to be effective. And this is going to be in a paper in the journal Computer Physics Communications in 2017. And now, what are extreme events? They are by definition high intensity, where they are localized in space and they are short-lived in time. If you think about a so-called Category 5 F5 tornado, it would have all of these properties. And in TensorFlow, fluid elements are being extended, they are being strained, and they are being forced to rotate around at very high rates. That's what we mean by extreme local deformation. I'm sorry. Okay, let me get back. Okay. So and we try to have a theoretical representation of these. We want to look at the ideas, look at the use of ideas of cell similarity. A very important quantity in dissipation in the study of turbulence is the dissipation rate. We're trying to see how the so-called scaling exponents that behave as a function of the different scale sizes. And this work is very important to have a very high Reynolds number. And on top of that, it's very important that we resolve the small scales well and that we provide adequate sampling. On blue waters, we were able to do the first 8192 cube simulation of homogeneous isotropic turbulence on a periodic domain with a focus on the fundamental issues. We also have some short data, some data at an even higher resolution, as I mentioned. And we are doing the mathematical simulations of turbulence. We have the Navier-Stokes equations. Here, this is similar to what we heard from the previous talk, a little simpler. We do not have to have the buoyancy terms or the rotation terms in the work that I'm presenting. And we are using Fourier pseudospectral methods, which involves a lot of fast Fourier transforms. They are very accurate, but they do have the disadvantage of being relatively computation intensive. So in order to scale the problem up to very large problem sizes, we have a massive parallelism. We have a two-dimensional domain decomposition that in principle allows us to use up to n square cores for an n cube problem. So on blue waters, we have done 8192 cube with favorable negative topology. We have used core wave fortran, which is very important. This is essentially one-sided communication. And on about 256K cores, our best timing was just under 9 seconds per time step, which scales very well if you compared to 30 seconds on 64K cores. The IO is quite fast. We can write a 4 terabyte checkpoint in about a minute. We have a post-processing code, so we have also some on-the-fly processing. We also have used the visit to provide scientific visualization, not of the entire 8192 cube domain though, but on the regions of interest. Well, we also have to run the simulation for many time steps, about let's say of the order 10 to the 5. And so, just to be clear, what do you mean by the dissipation rate? Twice the kinematic viscosity of the fluid times Sij with represented strain waves, or the symmetric parts of the velocity gradient tensor. And entropy is a measure of the anti-symmetric part. And Kolmogorov 1941 suggests that dissipation rate would represent the rate of energy transfer from the large scale to the small scales, and therefore it would be a determining parameter for the behavior that we see at the intermediate scales. But the story is not quite right. So in Kolmogorov 1962 suggests that we should insert take a look at the statistics of epsilon dissipation rate as a random variable, and we try to measure and try to average it over a volume of linear dimension r at some intermediate scale. So this integral is a volume integral can divide by volume, and this of course it means that the averaging has to be done in essentially over a three-dimensional volume, which is important but not easily done, and therefore they're not readily reported in either experiments nor even in the macro simulations. So, but we have figured out how to do that recently, and we have here on the left-hand side, we see results from averaging over a line, essentially one-dimensional, averaging over a cube, which is three-dimensional. And we can see that it's a substantial differences, especially in at the so-called intermediate values of R here. And we're looking using log scales. If we have a scaling law, there will be something like a straight line. We do see that for the three-dimensional averages, not quite for the one-dimensional averages, or that we're not really seeing the real story there. And and the data also also a Schwann function of the order of the moment. If you take epsilon r, or you take epsilon the fluctuation of r, if you have a large fluctuation raised to a higher power, then it will have a very strong effect on everything else. And now, in order to be quantitative, we like to be able to figure out what the scaling exponents are. So suppose if we have epsilon r to the power q, and then average divided by the global average to the power q, the proportional to r divided by eta. Eta is, by the way, is Kolmogorov length scale. If it's proportional to minus tau q, and want to figure out what tau q is, so what we do is to multiply the left-hand side by r over eta to the power tau q, and then we see whether we're going to have a flat range or not. So we're going to try a range of tau q's, and for different orders, with the values that we have come up with, we find that we do have a flat plateau, have a flat region, and the values are actually quite good, in quite good agreement with classical theory, which is known as normal, and these 5 numbers are quite close to the other 5. We still have to understand the data more compared with one-dimensional data from the previous literature. But we also would want to have a question to ask here is, say, how reliable are these results? We try to ask ourselves a critical question in some ways. For example, what about the effects of small-scale resolution? Because if you have we have very extreme fluctuations, we implies that there are fluctuations arising over dimensions much smaller than the grid spacing. So how do we, after doing the simulation, how do we find out how accurate the results are? One thing we can do is to say, let's refine the grid spacing. Let's halve the grid spacing, let's say. Do the simulation again with the same physical parameters, aiming at the same Reynolds number. So we'll be using performing a yet larger simulation. Unfortunately, this is going to be very expensive, as you might see. It may not always be feasible, and also the comparisons are going to be contaminated by statistical variability. We have some random variables on one particular grid resolution and another random variable or another grid resolution, so the statistics are going to interfere. And the other approach we can do is to take an existing data set. Think about it from the point of view of large unit simulation, perhaps. We would caution the grid spacing. We would go there and go into the data set, essentially as using essentially in the form of post-processing. We will cut off some of the high wave numbers and see how the results change. If the results change a lot, it means that our simulations, it implies that our simulations are not accurate. If the results change only a little, then it seems that we will be fine. So here I will focus on the middle block of here on the middle column and the one on the right. On the middle column, we actually have a 16K cube snapshot. And this is the result, similar to what we have seen before. And now we will reduce the resolution to from 16K cube to 8K cube. And the numbers change, as you might see here. Here the largest value 10 to the 17, and now they're down to 10 to the 13 or so. But then if we go to the intermediate range, we see that the numbers there are quite comparable. And in particular, the scaling exponents that we would arrive at it appears to be almost the same. So that shows that our results are actually robust. And then, before turning it over to Matthew, let me answer the question: why blue waters? When we think about blue water, we think about turbulence first as a grand challenge in science. The most we can actually argue that it may be the most complicated kind of fluid flows that we can think of. And there are many simulations in the past which have been compromised in some sense in the Reynolds number, in the accuracy, or in the resolution. And turbulence is very important to get a better handle on the underlying story. We can also think about turbulence as a grand challenge in computing. Turbulence was one of the problems performed on the Earth simulator in Japan, 2002. I'm sorry. That sort of triggered the so-called supercomputers arms race, at least as far as the turbulence community is concerned. So it took a long way. It took a long time for us to make progress from 4096 cube to 8192 cube, because it's 16 times more expensive. And if you do not have access to blue waters or a substantial allocation on a multi-platform machine, if the blue water staff were not as friendly to us as they were many of us going out of their way answering our desperate requests even in late night hours. If we don't have a 2 petabyte storage capacity, we may not be able to do so much. So I'm sorry if I went on too long.
Thank you very much. Thank you for sticking around for a few minutes. I know that we're very short on time, so I'll try to get through this part of the talk very quickly. What we've been focusing on for a little more than a year now is trying to develop some algorithms and study the physics of passive scalar mixing in turbulent flows, where a passive scalar is a substance or material property being mixed in a turbulent flow that does not dynamically affect the velocity field. We're going to focus on the regime of high Schmidt number mixing, where the Schmidt number is defined as the ratio of the kinematic viscosity of the fluid to the molecular diffusivity of the substance being mixed. When the Schmidt number is very high, experiments and simulations such as DNS are very challenging due to the stringent resolution requirements for the scalar field. And this is because, I'm just going to kind of skip ahead, because a much finer scale structure develops in the scalar field at high Schmidt number. And we're trying to illustrate that here with a couple of images from a simulation at a low Schmidt number of 8 versus a simulation at a high Schmidt number of 512. And if the picture is kind of visible on the screen, you'll see that there is a much finer scale structure at the high Schmidt number. And this requires a much finer grid resolution for the simulation. To kind of look at this from the view of the spectrum, what happens at high Schmidt number is that there is a pickup of the scalar spectrum at high wave numbers. You can kind of think of this as like a parameter sweep as you increase the Schmidt number. The spectrum picks up at high wave numbers, and we require finer grids to perform the simulations. So the general theme is, how can we exploit the physics of the passive scalar problem at high Schmidt number and the design of numerical algorithms and parallel implementations of those algorithms to simulate high Schmidt number mixing efficiently. So we're building on the work of our collaborator Toshiyuki Goto in Japan, where in 2012 he presented a numerical method where the idea is the scalar field requires a very fine grid resolution for its simulation, but the velocity field does not. So let's decouple both the numerical grid and the numerical scheme used for the velocity field and the passive scalar field. So the code is designed to solve the velocity field using the Navier-Stokes equations that Professor Yeung presented, using our existing pseudospectral code on blue waters, which relies on three-dimensional FFTs. But the passive scalar field is unique in that it does not require the numerical methods like FFTs for its solution. Instead, we can use a compact finite difference scheme which has much less communication requirements but still maintains high accuracy to solve for the passive scalar governing equation in a very efficient way. And I will skip over some details, but the basic idea is illustrated here in 2D, where we'll simulate the velocity field on a coarse mesh with a Fourier pseudospectral code. The scalar field will be simulated on a fine grid, and there will be an interpolation of the velocity field to form the advective and mean gradient forcing terms in the passive scalar equation. So to build on his work, Professor Goto designed the numerical scheme and the dual grid resolution approach. But we want to extend that and say, can we also exploit the physics in the parallel implementation of the numerical method? So to motivate the code design, let's consider an example problem which we've simulated on blue waters over the past year. We'll consider mixing in a turbulent flow, isotropic turbulence at a Taylor scale Reynolds number of 140, where in this case we're going to use a grid resolution of 1024 cube. Now, if we want to simulate a high Schmidt number scalar, say 512, the resolution requirements to perform a DNS of this mixing process will require an 8192 cube grid for the scalar field. So the computational requirements for these two problems are a little more than 2 orders of magnitude different in terms of the core requirements for the two flows. So the first attempt to develop a code for this type of flow might say, well, let's solve everything kind of in the same global MPI COM world communicator and maybe take our Fourier pseudospectral code and strong scale it up to 2 orders of magnitude greater cores than is actually required for the simulation. But what we thought about at the beginning was, well, let's just separate MPI COM world into 2 disjoint communicators, solve the velocity field in a very small subset of MPI COM world, transfer the velocity field to form the mean gradient and advective terms in the scalar field computation, which is occurring in a much larger communicator being run at the same time. Okay, so I'm going to have to go through this very quickly. But the main idea is that we're using a compact finite difference scheme. And it's kind of tricky if you want to use a compact finite difference scheme in a code that has a 3-dimensional domain decomposition illustrated here. The main reason why is that a compact finite difference scheme for the derivatives will couple all grid points along a given grid line. So there is like a linear system that needs to be solved for all grid points on a grid line. So how do you do that if you're partitioning the grid line across multiple processors? So we have to adopt a parallel algorithm to solve the compact finite difference linear system. And we will try to exploit this parallel algorithm to improve the scalability of our code by combining in a single subroutine the evaluation of derivatives in all 3 coordinate directions. I apologize that I don't have time to go over a lot of the details, but essentially what we will do is we will try to interleave the calculation of the derivatives in all 3 coordinate directions, overlapping communication and computation for these different coordinate directions, and try to improve the scalability at very large problem sizes. So there were 2 techniques that we attempted. One is to try to use maybe a traditional MPI non-blocking communication approach, where you might post a communication call for the upcoming coordinate direction, perform some computations, and then come back and make sure the results are ready before you need them. But we also thought that it might be interesting to try an approach where we use a hybrid programming approach, where you have MPI and OpenMP, and then we split off a couple of communication threads where the only task they will perform is communication during the computation, and we'll have a large nested parallel region that performs the computations that are required for the compact finite difference scheme. The basic idea is that we will create an OpenMP parallel region with 2 threads, where there'll be a communication thread, which will just kind of order up all the communication operations in sequence for each coordinate direction and kind of plow through them one by one when the communication call is ready after some computations have been done. This requires some features of OpenMP which might not be in say, widespread use. I'm not too sure. Maybe your code uses them, but we had to learn about these techniques in order to implement this. And if you have some questions, I can explain it more at the end. We have developed this code, and we have tested the scalability, and we're reporting that in the computer physics communication paper, where I'll just try to quickly illustrate. The open squares that you see here in the figure are the MPI blocking communication first attempt at the code. And as we try to improve the scalability, we tried many different approaches, non-blocking communication or using OpenMP threads. But the stars that you see, which scale very well at very large problem sizes, use dedicated communication threads and kind of explicitly separate the communication from the computation in the algorithm. We have been conducting many simulations for high Schmidt number turbulent mixing, and one of the main physical problems, aspects of turbulent mixing that we'll be looking into is the shape of the scalar spectrum. There's a lot of theory that goes into the shape of the scalar spectrum at high Schmidt number, and we will be testing to see how our results kind of agree or disagree with that.
Maybe the time is up. But I'd just to say that we have simulated turbulence at 8192 cube. We have studied turbulent dispersion. Reported as a Broad symposium last year. We're working on now turbulent mixing at high Schmidt number. And in the future, I would like to spend more time yet on analyzing the data. What I mean by computational turbulence laboratory, of course, is not a computer room, but rather a huge database that we want to share with each other. And we're going to move on also to MHD turbulence. Thank you.